Hi everyone, today a video on isomerization and specifically optical isomerization. So the first thing that's useful to think about is what are isomers generally? Isomers are compounds that have the same molecular formula but different molecular structures or different arrangements of atoms. So the overall formula of these molecules is the same, but they differ in the way that the atoms are arranged. And so we can break this down further into structural isomers and stereoisomers. So structural isomerism is where we have the same molecular formula, the same overall formula, but different structural formula, different actual molecular structures. So we have overall the same formula, for example, C2H6O, but the way that those atoms are arranged, the connectivity between those atoms is different. And so there are three specific types of examples. The first is functional group isomerization. This is where we have different functional groups that give us the same molecular formula. So the example I've given here is dimethyl ether and ethanol. So this is the example of C2H6O. Both of those compounds have that same molecular formula, but as you can see, the connectivity of those atoms is very different. And actually this is functional group isomerization because we have an alcohol in ethanol and our dimethyl ether is an ether. They're different functional groups. The next is position isomerization. This is where we have the functional group attached to the main chain at different positions. And so the typical example might be propan-1-ol versus propan-2-ol. That alcohol group is either on the first carbon or the second carbon. The overall molecular formula is the same for those two compounds, but they have very different connectivities of atoms, different structural formulae. And then finally, chain isomerism. This is where we have different arrangements of the carbon atoms in the chain of the compound. So this could be 2-methylpentane versus 3-methylpentane. The actual carbon chain is different. Then we have stereoisomerism. This is where we have two or more compounds that have the same structural formula but different arrangements of atoms in space. So what we mean here is that the atoms are actually connected in exactly the same way for both compounds, the same structural formula. But the way these are actually arranged in 3D space, the way they are actually arranged in space, is different. And so there are two types of this. There's EZ isomerization, or cis and trans isomerization. We've seen this mainly in alkenes. And so we think about Z isomers and E isomers. And so this is all to do with, we look for the heaviest groups that are attached in terms of atomic weight of our substituents based off the alkene. And we look to see if the two heaviest, let's say the two heaviest in this case are the red circles, whether those two heaviest groups are both either above or below the double bond, in which case they are the Z isomer, cis, or they are on opposite sides of the alkene, above and below, the E isomer, or trans. Remember that cis and trans is the kind of older notation for it. Really what we should use is the Z and E notation. But really the specific topic of this video is to look at optical isomerization, the other type of stereoisomerism. So what is optical isomerism? Optical isomers occur when there are four different substituents attached to one carbon atom. And what this results in is two isomers that have the same structural formula, the same connectivity of the atoms, but that they are non-superimposable mirror images of each other. They're not actually identical. Even though they have the same connectivity of atoms, they're not identical in 3D space because they have a different arrangement of those atoms. And so the easiest way to kind of think about this not from a chemistry point of view is to think about your hands or your feet. These are non-superimposable mirror images of each other. So if you take your left hand, take your right hand, put them out in front of you, they are mirror images of each other. However, if you try and stick your right hand on top of your left hand, and don't rotate it, don't sort of change it in any way, just simply place your right hand on top of your left hand, you'll see that they don't fit perfectly on top of each other. We say that they do not superimpose, they're non-superimposable. So we can then think about this almost from like a sort of cartoony type of view. So that central image, we have the different four substituents being represented by sort of four different shapes. So we have two kind of different sized circle shapes. We have a cylinder shape and we have a kind of triangle-based shape. And as you can see on the left-hand side of that image, if we have these kind of the holes for those shapes, on the left-hand side, those shapes fit perfectly into those holes. On the other side, though, we have the mirror image of that molecule. So imagine a kind of mirror in between those two molecules. We have the mirror image of each other. And so the one on the right is the mirror image of the one on the left. And you can see that we now don't have the correct functional groups in the right place, or correct substituents in the right place, to be able to fit into those holes. So you can see that we're trying to fit a circle-shaped substituent into a triangular hole, a triangle-shaped substituent into a circular hole. And so this is the idea that they don't superimpose. It's the same idea of putting your hands on top of each other. So if you put your right hand on top of your left hand, you have your right thumb kind of over your left little finger. They don't match up. And so then taking this to the actual chemical point of view, we could take the amino acid alanine, and we have two mirror images of this. Now the D and the L are just the how we name which of these isomers we have. But essentially we have alanine, which is an amino acid, and so we have a central carbon that is connected to four different substituents: a hydrogen, an amino group, a methyl group, and a carboxylic acid. And then you can imagine if we take D-alanine and we draw a kind of dotted line to kind of represent an imaginary mirror, we can then draw the mirror image of that. And you can imagine that if you just literally took the L-alanine and placed it on top of the D-alanine, put the carbons on top of each other, while the carbons and the hydrogens would match up, the rest of the functional groups would not be in the same positions. And so they are non-superimposable mirror images of each other. There's no way that the mirror image molecule can be put on top, superimposed, of the original molecule without breaking bonds. The only way that we could get it to work, so if we take back to the sort of cartoon image of those different shapes, on the right hand side we have our mirror image. The only way that I can get the triangle into the triangle hole and the circle into the circle hole is to actually break those two bonds. I can't simply rotate it by 180 degrees because then the blue cylinder would be at the back of the molecule and not at the front, and that wouldn't fit. And so the only way we can do it is to literally break the two bonds and reconnect them. So this is why this is a form of stereoisomerism rather than actual structural isomerism, because we haven't broken bonds, we have isomers that have the same connectivity, but just different arrangements of those atoms. And so a pair of molecules like this is called optical isomers, and they differ in the way that they rotate the plane of polarized light. And we'll see this in the next slide. It either goes clockwise or anti-clockwise. Now the really important thing when we talk about optical isomerization is the only way that this works is because we have four different groups attached to a carbon. That carbon is tetrahedral. And so when we draw out, if we're ever asked to draw out this kind of optical isomerization, draw out the mirror image forms of the molecules, we have to draw it in the proper tetrahedral arrangement. So that's two normal sort of plane bonds, a wedged bond, and a dash bond. Remember, the wedges and dashes just represent bonds that are kind of coming out of the page towards you and going into the page behind you. But we have to draw it out in that proper 3D tetrahedral arrangement, because if we just draw it out using just normal bonds and kind of almost in like a sort of perfect square arrangement, drawing the mirror image doesn't show that optical isomerization. So we have to draw it out in the proper 3D tetrahedral arrangement. And so this then brings us on to something called chirality. The optical isomers are said to be chiral, and we call the two isomers a pair of enantiomers. So enantiomers are a pair of optical isomers. So when we had the D-alanine and the L-alanine on the previous slide, we could say that those are enantiomers of each other. They are optical isomers, and they are chiral. So the carbon center that is bonded to four different groups is called the chiral center, or sometimes the asymmetric carbon atom. And quite often you'll see this indicated with a little asterisk. Sometimes not. But if there is a little asterisk, what that's telling you is that that carbon is the asymmetric carbon atom, or the chiral center of that molecule. Now, chirality is a property of asymmetry. Because we have four different groups attached, we can say that our molecule basically isn't symmetric. The only way that we can do anything to our molecule and get it back to its starting position, we can't kind of reflect it, we can't we can't do anything like that. The only thing we can do is just rotate it 360 degrees to get it back to its original starting positions. And chirality actually stems from the Greek word for hand. This kind of comes into the fact that your hands are also chiral objects. They are non-superimposable mirror images. Now, while the molecule can be chiral due to the lack of symmetry, never ever say that an atom is chiral. So never say that we have a chiral carbon atom. The reason is that atoms themselves cannot be chiral. An atom on its own, we can't talk about the symmetry of the atom. It's just an atom on its own. The molecule is what we talk about the symmetry for, and the molecule, therefore, is the thing that is chiral. So the carbon atom that we have our asterisks on, the carbon atom that is the thing that has 4 different things attached to it, we can say is the chiral center or the asymmetric carbon atom, but it's not a chiral carbon atom. It's a chiral molecule, but a chiral center or an asymmetric carbon atom. And so optical isomerization happens due to the fact that the isomers have different 3D structures. And this is why it's really important to draw it out, as we said on the previous slide, in the correct 3D representation. For carbon, tetrahedral with the wedge and dash bonds. Now, just on the bottom right there, we're showing the difference between chiral and achiral. Essentially, we have our achiral object, which is what looks like a bottle. And so if I have kind of a bottle and then I have a mirror, for something like that, we end up with the bottle on the right-hand side looking exactly the same as the one on the left. And if I superimpose the two of them, well, they match perfectly on top. And the reason for that, essentially, you can imagine almost turning that bottle around 180 degrees. It looks exactly the same. It has some symmetry. Your left and right hand, or your left and right foot, are chiral objects. They don't have that symmetry. We can't just rotate the hand by 180 degrees and get it to look the same, because if you rotate your left hand by 180 degrees, it's now the other side up. It's now the other way up. You've got your palm facing up rather than your palm facing down. And so if we have a mirror in between our left hand and right hand, and we try and superimpose, well, they can't be superimposed. And so some actual chemical examples here. The first one on the left, we could say was a chiral molecule. Because it has 4 different groups attached to that carbon, so the carbon is the chiral center, or the asymmetric carbon atom, but the molecule is chiral. And so this would exist as a pair of enantiomers, optical isomers. The second molecule along is an achiral molecule. This is because we don't have 4 different groups. We have a methyl group, a bromo group, but then also 2 hydrogen atoms. So anytime that we don't have 4 different groups, it's not chiral, it's achiral. And so this wouldn't exist as a pair of enantiomers. It would just exist as that singular molecule. The third one along is a chiral molecule again, because we have a methyl group attached, we have a hydrogen, and then we have 2 different alcohol groups. We have an ethyl group, CH2CH3, and a propyl group, the CH2CH2CH3 attached. So we have 4 different groups, and therefore it is a chiral molecule, and that carbon is the asymmetric carbon. And then finally, we have an example of an aldehyde here. This is an achiral molecule because, as you can see, the carbon atom technically has only 3 different groups. It has an oxygen, a hydrogen, and a methyl group attached. Now, technically, we call this kind of a molecule a prochiral molecule. A prochiral molecule stands for, if I was to add a nucleophile, for example, onto this molecule, if I was to add another group onto this carbon to make it into a tetrahedral carbon, that would then be a chiral molecule. Now, of course, that would only work as long as the nucleophile isn't a hydride anion, it isn't an H. But as long as it was something different, then that would become a chiral molecule by adding something to it. So that's something we call prochiral. But the take-home message is that it's an aldehyde or a ketone is an achiral molecule because we only technically have 3 different groups attached. So we talked a couple of slides ago about the difference between optical isomers being that they is the way that they rotate plane polarized light. And so light consists of vibrating electric and magnetic fields. It's part of the electromagnetic spectrum. So we have an oscillating electric field, we have an oscillating magnetic field. You can see on the diagram at the top, your electric field is shown in red, your magnetic field is shown in blue. And these fields are perpendicular at right angles to each other, and they're also at right angles to the direction of propagation, the way that wave is moving. And so we can think of it as waves with vibrations occurring in all directions. Now, if the light passes through a special filter called a Polaroid, this is similar to what happens in your sunglasses. Your sunglasses have Polaroid filters in. Then all of the vibrations will be removed apart from the ones that are in the plane. So, for example, if we have a Polaroid that is vertically polarizing, we get rid of all of the other vibrations except for the ones that are in the vertical plane. And so we now say that the light is vertically polarized. And this will be affected differently by different optical isomers of the same compound. And so we measure something called the optical rotation. If we start with completely vertically polarized light, we can actually see which optical isomer we have by shining the light through this, the isomer that we have. And we'll either see it rotate in one direction or rotate in another direction. And so we measure something called the optical rotation. We measure it using something called a polarimeter. And the way that we do this is we pass our polarized light. So we've already passed our just normal light through Polaroid filters. We've got our, for example, vertically polarized light. We pass that through two solutions of the same concentration, each containing a different optical isomer. Each of them contains one of the enantiomers. And so one solution will rotate the plane of polarization through a particular angle clockwise. This is what we know as the plus isomer. The other solution will rotate the plane of polarization through the same angle, but in the anti-clockwise direction. And so this is a really key thing, that one goes one way, clockwise, the other goes the other way, anti-clockwise. But if they are the same, if they're from the same molecule, essentially, if they are the pair of enantiomers of one molecule, that they rotate in either direction by exactly the same amount. So if they rotate it by 20 degrees clockwise, they're going to rotate, the other enantiomer will rotate the light by 20 degrees anti-clockwise. Now the plus and minus, as we talk about the isomers, only tells you about the rotation of light by the compound. So the plus isomer goes clockwise, the negative isomer goes anti-clockwise. The more correct IUPAC way of defining the optical isomers is to use what we call the R and S notation. So it's kind of similar to the E and Z notation in that we have our alkenes, and we can sometimes, if we have stereoisomerism in our alkenes, we can label it as an E alkene or a Z alkene. For optical isomers, for enantiomers, we can name them as either R or S. Now, actually doing this is way beyond A level, but it's kind of similar to the alkene isomer notation, that we're looking basically based on atomic weight again. But the really key thing to take away from this slide is that if we take our plane polarized light, either vertically or horizontally polarized, and then we pass that light through our enantiomers, our optical isomers, one will be rotated clockwise, the other rotated anti-clockwise, and by the same amount. So we can look at an example here of actually producing an optically active compound, something that exists as optical isomers. And many organic reactions that are used in synthesis produce optically active compounds, and they end up producing them in what we call a racemic mixture, or a racemate. This is where we have a 50-50 mixture of the two optical isomers. Now this could be, for example, where we've taken an aldehyde, we've added a nucleophile to it, we've created some tetrahedral molecule that's now chiral. And the reason why we often get 50-50 mixtures of this is because if we take a planar molecule, like an alkene, or a planar molecule like an aldehyde or a ketone, the nucleophile can attack from either above or below that planar functional group. And so because it can attack from above or below with equal probability, we end up producing a 50-50 mixture of the two enantiomers. And this is called a racemic mixture, or a racemate. And if we did the optical polarization experiment that we talked about on the previous slide, the effect of the two isomers would cancel each other out completely. So if I was only able to make the one isomer, the one enantiomer, I would see a rotation, say 20 degrees clockwise. If I had the other enantiomer just on its own, I would see a rotation of 20 degrees anti-clockwise. But if I have an exactly 50-50 mixture, well, the 20 degrees clockwise and the 20 degrees anti-clockwise cancels out. And so if we did this experiment, we would see no optical rotation at all. And that's one way that we can tell if we have something that should be optically active, whether we have a racemic mixture, is to do this polarimetry and to see whether we get any and to see whether we have any rotation. Now, if the mixture is not 50-50, it's something that we call a scalemic mixture. If only one of the optical isomers is produced, this is said to be a homochiral or an optically pure mixture. And there's currently a great deal of research into the field of what we call asymmetric synthesis. So we said that many organic reactions produce optically active compounds. Typically, you only want to actually have one of the enantiomers. Let's say you only want of that D and L aniline, maybe you only want the D aniline, but a lot of these reactions end up producing a 50-50 mixture. That's not so efficient because half of it is wasted already, as there's a lot of research going on at the minute in trying to produce only one of the two possible isomers. So looking at an actual synthesis of something, we have 2-hydroxypropanoic acid, more commonly known as lactic acid. This has an asymmetric carbon, a chiral centre, and hence is a chiral molecule. And so we can see the structure of it at the bottom left. We have a hydrogen attached, a carboxylic acid group, an OH group, and a methyl group. That's 4 different groups. So our carbon is the asymmetric carbon, that's shown in red. And then we have our chiral molecule. So this would exist as a pair of enantiomers. And so the synthesis of it produces the mixture of optical isomers. And so as you can see on the right, I've drawn out the 2 enantiomers, and I've drawn that mirror image, the imaginary mirror. Again, note how I've drawn it out as the proper 3D tetrahedral arrangement. So if we look at the synthesis of lactic acid, the first stage of it is we start from ethanal. So that's an aldehyde based on a 2-carbon chain. And what we're going to do is we're going to do a nucleophilic addition reaction of hydrogen cyanide to the CO bond in ethanal. Now, HCN is a really useful reagent in synthesis because it increases the length of the carbon chain by 1. We've seen this before in some of the other carbonyl videos, that using a cyanide anion is very useful because it increases the carbon chain by 1. Now, really, we wouldn't actually use HCN because HCN is a gas and it's very, very toxic, so it's difficult to deal with. We'd probably end up using a solution of sodium cyanide, for example, or potassium cyanide. And so we start from our ethanal, that's our aldehyde. Again, the aldehyde is a planar molecule. This is the really key thing, that because we're starting from a planar molecule, so this could be an aldehyde, it could be a ketone, it could be an alkene. Because it's planar to start with, this cyanide anion, the nucleophile, can attack from either above or below the plane of that carbonyl. So I've shown it on the mechanism below. There's a CN attacking from the top and a CN attacking from the bottom, and either one of those can occur. And so this ends up producing this 50-50 mixture of the 2 enantiomers, this racemic mixture. And so this mechanism that we're going to see here is a nucleophilic addition mechanism. We've seen this before. If you're not happy with it, go back to one of the videos in the carbonyl series where we talk about this. And so we're going to have an arrow from our negative charge on our cyanide anion, that's our nucleophile, to the delta positive carbon in our aldehyde, that's our electrophilic part. And our carbon already has 4 bonds. We have to break the weakest bond, which is the pi bond of the carbon-oxygen double bond. So we break that double bond open by having an arrow from the centre of the CO bond onto the electronegative oxygen that's happy to accept those electrons. So this creates our tetrahedral intermediate. We then have a proton transfer step. We pick up a proton from, in this case, the water, if we're doing it in a solution of sodium cyanide, for example. And so we end up producing what's called a hydroxynitrile. We have our nitrile functional group, our CN, C triple bond N functional group, that takes the priority. And then we also have our alcohol, our OH, but because the nitrile group takes the priority, we have to use the prefix hydroxy. So this is actually called 2-hydroxypropane nitrile. Then we have to do a hydrolysis reaction. This is the second stage of the synthesis. So we need to convert, remember the product, lactic acid, had a carboxylic acid group. We need to convert our cyanide group into a nitrile group into a carboxylic acid group. And so the way we do this is we just do a hydrolysis reaction. We react it with a dilute aqueous solution of HCl. And so the lactic acid that we then end up producing, it still has this chiral centre. We've introduced the chirality in the very first step by having that planar aldehyde reacting with our cyanide nucleophile, creating our tetrahedral 2-hydroxypropane nitrile. And because there's 4 different groups attached, an OH, a CH3, a CN, and an H, That's our asymmetric carbon. Our molecule is therefore chiral. And so therefore the chirality continues in this hydrolysis step. We still have 4 different groups attached. We have a hydrogen, an OH, CH3, and a carboxylic acid. So because we have 4 different groups attached, it's still chiral. We still have an asymmetric carbon. It's not affected by doing that hydrolysis reaction. And so we still have the racemic mixture, the 50-50 mixture. So it's often the case that when we do this kind of synthesis ourselves, that the synthesized molecule we have, the chiral center, ends up as a mixture of the 2 optical isomers. It ends up as that racemic mixture. However, the same molecule that's produced in living systems naturally will often only be present as one isomer. So for example, all of the naturally occurring amino acids, except glycine, so 19 out of 20 of them, are chiral. But actually, only one of each pair of enantiomers of those, only one of each pair of those isomers, is formed in nature. Nature only forms one of the enantiomers, whereas we as human chemists would normally have to form 2 of them, form that racemic mixture. And this is because the molecules are being synthesized in nature by enzyme catalysts. Now, we've talked about enzymes in the biological chemistry series. Enzymes are incredibly shape specific. They have an active site that has a very, very specific shape. And so actually the way that they are made is such that only one of those enantiomers is able to fit into the active site of the enzyme. Because of course, remember that the stereoisomers, these enantiomers, they're different because they have the same connectivity of atoms, but a very different 3D shape, a different actual arrangement of the atoms in space. So the enzyme, because of the shape, how shape selective it is, it can only catalyze the formation of one of those enantiomers. Now, some drugs are optically active compounds as well, and for some purposes, a racemic mixture of the 2 optical isomers will suffice. So it doesn't matter that we produce a 50-50 mix of both of them, it could just be that we can just sell that straight away. However, other uses, we only want one isomer. And the reason for this is because sometimes only one of the isomers is actually active as a drug. So if we put the racemic mixture in, well, we're only getting kind of half the effectiveness because only half of that mixture is active as a drug. We're wasting the other half. Or it could be that actually the other isomer has very, very detrimental effects in the body. And it can be quite a weird thing to think that actually, as we'll see on the next slide, we have some examples. One enantiomer may be very, very useful as a drug. The other enantiomer may have some really, really horrible side effects in the body. And so many drugs work by a molecule of the active ingredient fitting into an area of a cell called a receptor. And it's like a piece in a jigsaw. Again, it's very kind of shape selective. One fits perfectly into the kind of the hole, if you like, of the receptor. And so receptors have 3D structures, and so much like the enzymes we just talked about, they're very, very, very shape selective, and so only one of the optical isomers, one of the pair of the optical isomers will fit. Only one enantiomer is able to fit. And so in some cases, the one optical isomer is effective as a drug, the other is inactive, or sometimes the other is potentially very dangerous. And so there are a couple of options we can do. We can try to separate the 2 isomers, but this is very difficult and very expensive. Now, earlier on, we said that optical isomers, we can differentiate between them by seeing how they rotate plane polarized light. We can do optical polarimetry. Now, that actually is the only difference between optical isomers. The only way we can tell them apart is through doing this polarimetry to see whether it rotates the light to the clockwise direction or to the anti-clockwise. But optical isomers actually have identical chemical properties. They actually only differ in that plane polarized light rotation. They have the same melting point, boiling point, the same hydrogen bonding ability, and so it means it's very, very difficult to start to separate these out through maybe doing a recrystallization or by doing chromatography, column chromatography, for example. Because they have the same chemical properties, it's really, really difficult, almost impossible to separate them. We can sell the mixture as a drug. However, that's wasteful because half of it is inactive. It could be the other half is very dangerous as well, so sometimes that's not possible. Or we can design an alternative synthesis of the drug that makes only one required isomer. And this is really where the research is at the minute, trying to make only one of those isomers to begin with. And so some examples of these. The first is the really common one, ibuprofen. I feel like everyone probably has taken ibuprofen at some point for a headache or just general aches and pains. This actually has an asymmetric carbon. It's a chiral molecule, and I've noted that with the red asterisks. You can see we have 3 different groups attached to that. We have some sort of benzene ring that's substituted. We have a methyl group, we have a hydrogen, and then we have a carboxylic acid group. And this is actually sold as a racemic mixture. That's quite weird to think that kind of one of the most popular drugs, ibuprofen, is sold as a 50-50 mixture, where one of the enantiomers works, the other one is just inactive, and so actually it's quite wasteful. Another one on the right here is naproxen. Now this is an example where one of the isomers is very good at acting as a drug, the other actually is very harmful, because the one isomer treats arthritic pain, the other one causes liver poisoning. So obviously you really don't want to be selling that as a racemic mixture. You need to only be getting the one isomer that treats the arthritic pain. And we can see there that there's an asymmetric carbon. We have this kind of aromatic group attached on the left. We have a methyl group, we have a hydrogen, and we have a carboxylic acid group. And then finally, probably the most well-known example of this kind of optical isomerization going wrong is in thalidomide. Now, this is where one isomer effectively treated morning sickness in pregnant women was a sedative, so it was very useful for pregnant women. It allowed them to sort of not feel the pain so much and to cure morning sickness. However, the other enantiomer caused really, really serious and unusual birth defects. And this was partly a problem in sort of screening these and not understanding how the enantiomers worked properly at this point. And so this was sold originally as a racemic mixture. They didn't realise that they had the detrimental properties, the birth defects. And so this was given to lots and lots of pregnant women. They didn't notice any side effects, obviously. They just had the kind of treating the morning sickness. And then when the babies were born, they were being born with kind of disfigured limbs, without arms, without legs. And so that's why it's really important to properly understand the properties of both of the enantiomers and to see if it's a detrimental effect, to only sell it as the one enantiomer, to try and separate that racemic mixture. So, time to have a go at some questions. If you'd like to have a go at these questions, pause the video and the answers will be on the next slide. Potentially we have some series of questions here all about optical isomers. So the first question here was telling us about a reaction of butene with hydrogen chloride, and this formed a racemic mixture of the stereoisomers of 2-chlorobutane. So to name the type of stereoisomerism, well, this is optical isomerism, and give the meaning of the term racemic mixture. Well, a racemic mixture is a 50-50 mixture of enantiomers, of optical isomers. And then state how separate samples of the stereoisomers could be distinguished. Well, we distinguish them again. Remember, they have the identical chemical properties. The only way we can distinguish the two enantiomers is through the optical polarimetry. We're going to see how they rotate plane polarized light. One will rotate it in one direction, the other will rotate it in the other direction through equal amounts. And the reason that this produces racemic mixtures and optical isomers is because we're starting from a planar molecule, an alkene, butene. We have our electrophilic addition reaction, so our hydrogen goes onto one carbon, our chlorine goes onto the other carbon. This produces 2-chlorobutane, and you can see that we have essentially the second carbon in from the left is the asymmetric carbon, and that's what makes the molecule chiral. We have a chlorine attached to hydrogen, a methyl group, and then another carbon chain. And so that's a chiral molecule, or we can say that's the asymmetric carbon. And so the reason for is that the carbocation is planar, and so when the HCl sort of adds on to the alkene, this can add from either essentially above or below the carbocation. So we've started with a planar alkene molecule. We've done our first step of that electrophilic addition, which is to add our hydrogen onto one of the carbons. This produces a carbocation. The carbocation is also planar, and then in this case the Cl- that can attack from either above or below the plane of that carbocation with equal probability. It's equally likely, hence we end up with a 50-50 mixture. If it wasn't equally likely, then we wouldn't have a 50-50 mixture. We might have, for example, a 70-30 mixture, and remember that's called a scalemic mixture. But if it's equally likely, as it is in this case, we have a racemic mixture, 50-50 mixture. Then the second question was to, we had a number of reaction schemes. The first one was to name compound J. So we look for our longest carbon chain. In this case, it's 4 carbons long. starting from the carbon that has the OH group on. We also have a methyl group that is branching out of the chain. And so this is an alcohol, no other functional groups, so we use the suffix -ol. We need to number where our alcohol is, it's on the first carbon, and we need to number where our methyl group is, that's on the second carbon. And so this is 2-methyl-butan-1-ol. Second question then was to say that compound J exists as stereoisomers. Name the type of stereoisomerism. This is optical isomers. Remember that stereoisomerism is either EZ isomerism, which we find in alkenes, or it is this optical isomerism, which we see if we have 4 different groups attached. So the EZ isomerism, an example of this would be the butyene at the top. I haven't written it on, but this is technically the E isomer, the butyene, our 2 heaviest groups. The 2 methyl groups are on opposite sides of the double bond, so it's the E isomer, E-butyene. That's our EZ isomerization. The other form of stereoisomerism is our optical isomerism, where we have 4 different groups attached to a carbon. And we have this on this alcohol because we have a hydrogen, an ethyl group, a methyl group, and then our CH2OH group. And then finally, it was to draw the structure of an isomer of K, which shows stereoisomerism. Now, K was an alkene, so when we think about the isomers that show stereoisomerism, again, it's the E and Z isomer, so we need to draw out our Z isomer and our E isomer. And so to draw out our isomer, remember that we can't have EZ isomerization if we have 2 of the same group attached to a single carbon. So the alkene in the question has 2 hydrogens attached to the 1 carbon. That doesn't exist as stereoisomers. There's no EZ isomerization possible there. But if we rearrange the sort of the connectivity of these atoms in such that we put the CH3 group onto the other carbon, then we can either have the ethyl group and the methyl group being both above or below, that's the Z isomer, or one above, one below on opposite sides, and that's the E isomer. So thank you for watching this video. You can find more videos like this on my YouTube channel. If you found it useful, please consider leaving a review on our tuition website. I offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, always feel free to drop me an email. I'll be happy to help.